handle about it? Jan, bisa share presentasi. Pak Merah mau share presentasinya.
Still cannot share my screen.
How about now?
Let me check. Yes, is it possible? Okay. So you can see?
It's very clear.
Okay, thank you. Very good morning, everyone. I'm Mehran from Department of Chemistry here at University Malaya. Actually, I'm truly grateful for this opportunity to share my knowledge and research on green hydrogen production by water electrolysis. So hopefully we have a good discussion here. I would like also extend my special thanks to Prof. Rickson for organizing this webinar. So you are all aware of the global challenges comes from fossil fuel. For example, the environmental pollution like nitrous oxide or sulfur oxide always emitted in the atmosphere, or a soaring of carbon footprint like carbon dioxide. And also the serious health problem. Many people, many people, because of heart attack or some cancer, yearly died only because of the pollution. So here, first of all, I would like to share with you some statistical data regarding this matter. So first of all, the global demand for energy consumption continuously increasing by 1.3% each year because of three important factors. First of all countries deal with global economic growth and also growth of population. If you have a look at your country, Indonesia or Malaysia, compared to 10 years ago, the population continuously increasing. And this population also uses the advanced technology. If you visit your, for example, village, you see that many villagers right now use the mobile phone, computer, laptop. They have their own cars. So all of this technology need energy for production. So it means that global demand for energy is continuously increasing in the world. This graph shows the consumption of energy and demand for energy based on the different year. The x-axis shows the year and the y-axis the demand for energy in terms of BTU. You know that BTU is the British unit for heat energy. 1 BTU is equal, the energy is needed for 1 pound of water increase its temperature for 1 Fahrenheit. And quadrillion means 1,000 million. So it means that 10 to power 15. So if have a look at this graph, the red graph shows the nuclear energy, I think, because I cannot see here. And the green one related to renewable energy, blue one, I think natural gas, and black coal, and red one, petroleum and other liquid like gas oil or oil or something like that. So if you have a look at this graph, you see that so this graph disappear. Yes. So you see that before 2030, actually the renewable energy demand constitute a significant smaller share compared to other fossil fuel. And this share reach to parity around 2030. And after that, after 2030, of course, this demand increasing. And around 2045, surpass all of the fossil fuel energy. So, because of this consumption of energy, every year, 36 billion ton carbon dioxide emit into atmosphere. And 90% of this 36 billion ton attributed to consumption of fossil fuel. So here, in this graph, you can detect the consumption, the emission of carbon dioxide because of consumption of fossil fuel. For example, in 2010, the natural gas emit around 7 billion ton carbon dioxide into the atmosphere. 25% of this 36 billion ton comes from some industrial that produce the electricity or heat generation. And 20% of this 36 billion ton is related to industrial for process of other product. And 20% comes from the transportation. And remain comes from other purpose. For example, some residents or some village, I mean, for example, use the jungle wood or burning of jungle, emit the carbon dioxide into the atmosphere. So now my question is, how we can tackle these huge issues? So this is very huge issue for our society and our nations. How we can tackle these huge issues? I believe that the answer is easier and the answer is clear. We must transition from fossil fuel energy to green energy, such as hydrogen. This is the clear answer. But I believe that the path to this solution is demanding, is not easy. We have to change many things in the world, especially the attitude of politicians or people. This is very important. So generally, we have two different methods for production of hydrogen. The first method is known SMR, steam methane reforming. This method is based on a fossil fuel. Based on this chemical reaction, you see that the methane at high temperature and pressure react with steam and produce hydrogen. But this hydrogen is not green hydrogen because first of all, this method uses the fossil fuel and also the byproduct is significant amount of carbon dioxide. So around 17 million ton hydrogen is produced annually in the world. And 50% of this 17 million tons dedicate to ammonia synthesis. And most of this hydrogen production comes from this method, comes from SMR method. And around 830 million ton carbon dioxide emitted into atmosphere, only because of production of hydrogen using this method. So this means that this method is not green method for production of hydrogen, although right now, most of the hydrogen is supplied by this method. The second method is known water electrolysis or water splitting. This method is based on water. So this method hinges on three essential components: the water, the electricity, and the electrocatalyst. So among these three components, electrocatalyst is very important. It acts as a vital bridge, like a vital bridge, convert the water into hydrogen. So playing an important role, the electrocatalyst. So electrocatalysts, during the three fundamental mechanisms produce the hydrogen. We call Volmer, Hayrovsky, and Toffel. This is the fundamental mechanism. Briefly, Volmer deals with absorption of water, and Hayrovsky deals with desorption and production of hydrogen, and also Toffel also. So it means that in Volmer step, water adsorbed on the surface of electrocatalyst, and during the Hayrovsky step and Toffel step, this hydrogen is formed on the surface of catalyst. So actually, when water wants to adsorb on the surface of catalyst, we have some confinement. This water adsorbs on the special surface of catalyst we call active site. This active site actually is tunable. We can increase, we can decrease, we can change the position of active site, for example, from center to corner or so on. So how we can tune this active site? Actually, active site is function of band gap or band energy of electrocatalyst. So we know that band energy also is function of many chemical or physical properties. We change in, for example, in morphology, or change in composition, or change in crystal structure, band structure will change. And this one affect on active site. So briefly, active site is tunable. So briefly, electricity excite the electrocatalyst and produce the electron. Water adsorb on the surface of electrode and react with this electron and produce the hydrogen radical. And after that, during the Hayrovsky and Toffel, this hydrogen radical produce the water. So the reaction is very simple. This reaction can take place in both acidic and alkaline media, but Volmer-Toffel reaction is common in acidic media, but Volmer-Hayrovsky is common in alkaline media. So what is the challenge in this technology? I would like to discuss a little bit about this challenge. Already I mentioned that this technology lies on. Prof, could you please turn off your?
Coba ditanya dulu SK-nya, maunya dia sudah ada yang agendakan rapat ini.
Could you please turn on? Yes, turn on.
Gimana ya? Karena kalau undang yang lama aja kan nggak bisa juga. Kan harusnya pimpinan yang baru ada semua gitu loh maksudnya. Gimana sebaiknya? Ya, coba minta dipercepat. Kemarin dia udah ke dekanan.
Professor, could you please turn off your microphone?
Gitu. Udah yang kemarin kan udah koordinasi.
Okay, thank you. Okay, so this technology actually lies on three essential components. Already I mentioned that water, electricity, and electrocatalyst. So now my question is that the real challenge comes from water or electricity or electrocatalyst. Actually, water is not challenge here. Although for this technology, we have to use the pure water or drinking water. But and we know that, for example, many countries, suffer from the lack of drinking water. Of course, in Malaysia or Indonesia, we deal with too much, rain, and then we don't have problem with water. But in many countries, like Middle East country, actually drinking water is problem. But they access to at least seawater or ocean. So no, this technology works with seawater. For example, if we couple the water purification technology with hydrogen production technology, then directly we can use the seawater. So it means that for this technology, till now, water is not challenge. Electricity also is not challenge, because right now we can use the renewable energy, like for example, solar power or sun power or so on. The real challenge comes from electrocatalyst in this technology. The real challenge comes from electrocatalyst. So right now, platinum shows the best electrocatalytic activity. This is the LSV curve of platinum. So its onset potential is around positive 14 millivolt. Its over potential is around negative 15 millivolt. Its Toffel slope is between 35 to 40. Everything is perfect. But unfortunately, platinum suffers from huge challenges. First of all, we know that the platinum is very expensive. And it's faced with limited availability, like a gold. So if we would like to produce tons and tons of hydrogen, so we need 2 tons and tons platinum. So providing this huge amount of platinum is challenging. But most important thing is that, unfortunately, platinum faced with propensity for degradation, especially in alkaline media. So we have to change very fast the electrode. And also its stability and durability is very low. So of course, at the beginning shows the best electrocatalytic activity, but this electrocatalytic activity dropped so fast. So that's why we have to think a novel electrocatalyst. This novel electrocatalyst should actually overcome these challenges. So first of all, the price, and the second one, durability and stability. We have to design like this electrocatalyst. So another challenge, I think, arises from the final cost of hydrogen production. If we want to produce hydrogen using SMR method, then if we suppose the efficiency of 1 kilogram hydrogen is equal, for example, 1 liter petroleum. So right now, the production of 1 kilogram hydrogen using SMR has cost around $2.5 or $2.1. So I don't know how much is the price of petrol in Indonesia, but in Malaysia, for example, 1 liter petrol is around 50 cents. So this difference between price is too much, still too much. And if we want to produce hydrogen using the water electrolysis, then the price of 1 kilogram hydrogen is around $1.5. If we suppose that the price of 1 kilowatt hours renewable energy is around 2 cents, but we know that right now is more than 2 cents. So still $1.5 is expensive compared to fossil fuel. But I believe that this price is not expensive. The price of fossil fuel is very cheap. For example, in my country, Iran, the price of petrol is 10 cents per liter. This one, I think, controlled by some country. I'm sure 10 years later, 20 years later, when population increased, the demand increased, and the source of fossil fuel decreased, this price dramatically increased. Right now, I think this price is not real price for fossil fuel. Another challenge comes from storing. We know that hydrogen is gas, so need to compress hydrogen, and we store in some tank. So this one also provide extra cost. And finally, related to the safety of hydrogen because of flammability. So these are challenges related to green hydrogen production that we face in our world. So another question is that whether water splitting can be applied on industrial scale or no, just we use as a lab scale in our laboratory. The answer is affirmative. The answer is positive. Right now, many industrial methods exist for producing the green hydrogen. Here, I bring you 4 different methods for production of hydrogen in industry. Alkaline water electrolyzer, AWE, anion exchange membrane water electrolyzer, AEMWE. The third one I cannot see, I think the proton membrane electrolyzer, and fourth one, proton conducting ceramic electrolyzer. So briefly, I can classify these 4 technologies in 2 different groups. The first and second one is based on circulation of OH negative from cathode to anode. So it means that these 2 technologies work in alkaline media. And the third and fourth is based on circulation of hydrogen ion from anode to cathode. So it means that these 2 technologies work in acidic media. And also there is a little bit different between the first and second technology. Actually, the first technology is based on lab scale. We test our, electrocatalyst based on this technology. The strength of alkaline should be around 20% to 30%. Mostly they use KOH or NOH. But in the second one, means AEMWE, anion exchange, the concentration of alkaline decrease. It means that they use the weak alkaline solution. this technology. So already I upload one short video from YouTube. This video shows that the advancing in hydrogen production in industry.
Okay. Hello?
You see the video, Prof?
Not.
Oh.
Maybe you first close
Okay.
your PPT and then
Okay.
move to the video.
Computer is hang. We need time. You see?
Yes.
Okay.
Okay. Now run.
Okay. So you see that this simple chemical reaction, how come into the industry and produce the green hydrogen. So in next slide, I would like to introduce you some novel electrocatalysts. Right now in my research group, they use this novel electrocatalyst to production of hydrogen. Some of my students are master and some of them are PhD. They are working on this novel electrocatalyst. I'm sure you all know about the 2D material. Actually, 2D material is a special morphology of nanomaterial. That is, the thickness is very important. The thickness is around a few atoms or less. So we deal with a broad variety of 2D material. For example, graphene is the famous 2D material. Transition metal dichalcognight, TMDS, MXene, hexagonal boron nitride, and so on. So actually, the importance of 2D material started after graphene is discovered in 2004. So after discovering of graphene, many other 2D material, more than 2,000 different type of material already predicted in theory. There exists in 2D material, but still they couldn't synthesize it. After production of graphene, they understood there is not, for example, the limitation on van der Waals bonding, or for example, hydrogen-hydrogen bonding for example, production of 2D material. Any material with simple bonding also can produce the 2D, like for example, borophene, silicon, germanium, phosphorus. There is not any van der Waals bonding in this chemical, or for example, hydrogen-hydrogen bonding. So the 2D material have many advantages, like for example, high surface area, low atomic thickness. But the most important thing, electronic properties, make it interesting for researcher. So we know that graphene is the best, is perfect, is super thin, super strong, flat, flexible, transparent, conducting, and so on. The question is that why we need to discover other 2D material. Generally, I classify this 2D material in two different groups, graphene and 2D material beyond graphene. Actually, I classified these two ones. Why? Of course, graphene is the best, but unfortunately, graphene is not semiconductor. Its behavior is like metal. That's why we cannot use graphene in many electronic or optoelectronic device, because we cannot tune their band gap. That's why we need to discover new generation of 2D material that their band gap is tunable. So we have broad range of choice for 2D material beyond graphene. For example, if we want to use in optoelectronic device, for example, we need the insulator. Then we can use, for example, hexagonal boron nitride. If we need, for example, conductive layer, we can use the graphene. That's why we need to discover new generation of 2D material. So here I bring you the wide range of 2D material. For example, niobium selenide has potential for superconducting. Vanadium sulfide or vanadium oxide has potential as a metal, half metal like chromium oxide, chromium sulfide, semiconductor like molybdenum sulfide, tungsten sulfide, and insulator hexagonal boron nitride. So we have many choice. If we synthesize this material as a 2D, we have many choice to use them in optoelectronic device or energy conversion device, or for example, hydrogen production device or sensor device. So my research group actually work on 2D transition metal dichalcogunide, TMDS. We know that the TMDS, unlike graphene, has the formula like MX2. M is belong to transition metal, commonly from group 5 to 7. And X is chalcagon atom, like for example, sulfur, selenium, tellurium. So any composition of this two metal is known TMDS. For example, molybdenum sulfide, molybdenum selenide, molybdenum telluride, or rhenium sulfide, rhenium selenide. All of this material are inside of TMDS. So the monolayer of TMDS consists of 3 atoms. Transition atom layered inside of 2 chalcagon atoms. So this 3 atoms shows the monolayer. And between each layer, we have van der Waals force. But between each atom, we have covalent bond. So we can decrease the thickness of this atom with different morphology, with different method of synthesis. About the band structure of TMDS is between hexagonal boron nitride and boron carbon nitride. If we suppose hexagonal boron nitride, the band gap is around 5 electron volt, the boron carbon nitride is around 1-2 electron volt. Then the TMDS between 1 to 2.5 electron volt, the band gap. And of course, graphene is 0 electron volt. So if we produce the monolayer TMDS, their band gap is direct band gap. But for bilayer, triple layer, or so on, they are indirect band gap. So my research group synthesized these two TMDS using two different methods. First, they focus on hydrothermal, and the second group used the CVD for production of TMDS. Especially they focus on molybdenum disulfide. We know that using the hydrothermal method, we mix some precursor of material in some solution, and then they react at high temperature, the boiling temperature above of the solvent. For example, if we mix in water, the boiling temperature should be above 100. And during this reaction, we can produce this 2D material. And also we can directly deposit this 2D material on the surface of substrate. For example, we can use nickel foam or ITO and leave it inside of autoclave. And then directly we can grow this 2D material on the surface of electrode. So two of my students, Mina and Ekida, actually already work on synthesis of molybdenum disulfide using the hydrothermal method. Mina was a master student in our department, but 1 year ago, she graduated, and now she's the PhD student at University of Calgary in Canada. And Ekida still is with us, but she graduated from master. They synthesize molybdenum disulfide using hydrothermal method. The morphology is two-dimensional, like a graphene, but the wrinkle is, there is some wrinkle in the surface of molybdenum disulfide. The dimension was around 1 micrometer, average 1 micrometer, the dimension of this 2D material. For determination of the number of the layer, they tested the Raman. Raman of molybdenum disulfide shows two distinguished peaks, E12G and A1G. E12G is around 384, and A1G is around 407. But the distance between these two peaks shows the number of layers. This is interesting. If the distance between these two peaks is around between 80 to 20, 80 to 19, so it means that these sheets are monolayer. If the distance of these two peaks is around 22, this is bilayer. And if between 22 to 24, 23, like that, then this is triple layer. And more than 24, this is multi-layer. It's like a bulk. So for them, the distance was around 23. So it means that they produced a triple layer molybdenum disulfide. It's expected because using the hydrothermal, it is not possible. It's very tough. You produce the monolayer of molybdenum disulfide. But for CVD, actually, the production of monolayer is easier. So they tested also the XPS result to prove that the purity of sample. There is not very strong peak related to any oxide in their synthesis. So it means that they produced a pure molybdenum disulfide. This is the difference between CVD and hydrothermal. Unfortunately, on CVD, always we deal with oxide. The thickness is very nice, but purity is not very nice. But in hydrothermal, the thickness is so-so, but purity is better. So Mina applied the molybdenum disulfide by platinum for hydrogen production. Both of them think that how they can decrease the cost and also increase the stability. That's why they use molybdenum disulfide beside the platinum. Of course, because you disperse the platinum on the surface of molybdenum disulfide, then the amount of platinum usage decrease. So because the content of platinum decrease, the cost decrease. And also their stability because of the presence of molybdenum disulfide increase. So they decorate the platinum with size of 2 nanometer on the surface of molybdenum disulfide, and then they utilize this composite for HER, for hydrogen production reaction. So if you have a look at this graph, this black one is related to commercial PT. And then Mina think that maybe the content of platinum affect on HER. And he tried to optimize the amount of platinum on the surface of molybdenum disulfide. He tested many ratios. And finally, he optimized the HER based on the amount of PT. He chose 3 different amounts with 60 microliter, I think 90 microliter, and 120 microliter for chloroplatic acid solution based on precursor. And she observed that the amount of platinum has effect on HER, on LSV. So he concluded that if we increase the amount of platinum on the surface of molybdenum disulfide, maybe this extra amount of platinum lead to agglomeration of this platinum, and the conductivity may be decreased, or size of some nanoparticle increase and affect on the electrocatalytic. Then she tested using the EIS, and she observed that the conductivity will change and as relate to the amount of platinum content. So she succeeded to publish her research on nanoscale research literature. I think this is the Q1, impact around 5. Ekida synthesized the ternary composite. She introduced another component, cobalt oxide. She synthesized the molybdenum sulfide, cobalt oxide, platinum. So here, the sheet is molybdenum disulfide, the cube is cobalt oxide, and the small particle of platinum decorated on the surface of cobalt oxide and molybdenum disulfide. She also tested for HER. And based on her result, you can see that the presence of cobalt oxide and platinum affect on HER electrocatalytic activity. And also she tested for stability and durability. Compared to commercial platinum, actually the composite shows the higher stability and durability. After 1,500 cycles, still the composite shows the good efficiency. And also after 50K second, it means after 13 hours, 13 hours, the composite still was stable. She published her research in Electrochemical Acta, I think 3 years ago. This is also a very good journal, impact around 6.5 or 7. Currently, my 2 students, master student, Badrul and Nitya, they are working on growing up molybdenum disulfide using the CVD method with collaboration with Dr. Go in physics department. We know that in the CVD method, we use the oxide precursor of material like molybdenum oxide and sulfur. And then in high temperature, they evaporate and react, and the molybdenum sulfide produced on the surface of electrode. But already I mentioned that the CVD challenge is related to purity of composite. Unfortunately, still the result is upcoming. The result is not very nice. So actually they produced a monolayer of molybdenum disulfide, but the purity is not very nice. Still we can detect some molybdenum oxide beside the molybdenum disulfide, but still research is ongoing. Another, my PhD student, Najwa, work on synthesis of manganese silicide for HER. She's the PhD student in physics department. She synthesized MNSI on the surface of silicon wafer. And he optimized its morphology and composition using the change in the pressure inside of the CVD chamber. So she investigates systematically the effect of pressure on the morphology of MNSI. And finally, she applied this new composite for HER, for MNSI. Actually, this is MNSI nanowire for HER. Its result is comparable with molybdenum disulfide, but still cannot surpass the platinum. Of course, platinum is perfect, but the stability of MNSI she tested, the stability was nice. She published her research in ACS Applied Nanomaterial 3 months ago. This one also very nice journal. You can find the detail of her experiment in this journal. Okay, thank you so much. I'm ready for more discussion about the HER, hydrogen production.
Thank you so much, Dr. Meran.
You're most welcome.
Yeah, very nice presentation. Yeah, this morning. So you already expressed very beautiful how to produce graphene, produce hydrogen, right? In a lab scale and also industrial scale. So how about the participants? Do you have some comments or question to Dr. Meran? Okay. Meanwhile, the participants deliver the question. I have some question maybe, Dr. Meran. Yeah.
Okay.
This is very hot topic. Yeah. Many people already, I think, succeed to produce hydrogen by splitted water. Yeah, using the catalyst, of course, right? The next question is, how do you decide the catalyst to split H2O be hydrogen and oxygen?
Actually, part of all related to band gap, because the bonding of water is around 1.2 electron volt. So you have to use some semiconductor, their band gap is around this one. And also they have the good electrocatalytic activity for production of hydrogen. We know that already I mentioned that this is the reaction is look like so simple, but in practical is so complicated.
Yes.
Yes. And always the active site play an important role. Some materials shows the good, ability for absorption of water on their active site and produce of hydrogen. So the TMDS shows that they have the ability for production of hydrogen. Already we saw many publications in Nature or Science, they reported on the ability and potential of TMDS for production of hydrogen. Then we decided to test this material. We saw very good stability also with this material, and also because of their 2D material, 2D nature, their nature, the production of some composite is easier than other material, the composite with, for example, metal, non-noble metal, or for example, we have many choice with some oxide, like for example, cerium oxide. Now my groups work on production of novel material using cerium oxide with TMDS, or for example, with other material. So yes, the answer is that everything depends on their nature, the nature of 2D material. So for example, maybe the hexagonal boron nitride doesn't show the good response for HER.
Okay. The next question, yeah. So if a participant has a question, you may directly interrupt me, right? So the next question, after we succeed to split it like methane or water, how do you collect the hydrogen?
Actually, we just confirm the production of hydrogen. So if you want to, for example, measure the amount of hydrogen production, you need extra equipment that should be attached to your cell. For example, using the HPLC, we can determine the amount of hydrogen production. So our work is, because it's based on lab scale, we just test for hydrogen production and we will confirm that this material has potential for commercialization or not. This is our duty in the lab. Of course, if we want to bring in industrial application, so we need to attach our cell or our equipment to another instrument like HPLC or like that. And then we can determine the amount of hydrogen production. So right now, unfortunately, in our lab, we don't have any HPLC that's attached to our cell. So just we work on the potential of material for hydrogen production using the LSV. And for us, two parameters is very important. First of all, the over potential should be shift to lower potential. So it means that in lower, the potential, you can produce the hydrogen. So the cost of the hydrogen production decrease because you need less to use that electricity. Okay, and then actually we will focus on the stability. How we can improve the stability compared to pure platinum or commercial platinum. This is to our objective. We work on cost and stability.
Okay. Thank you, Dr. Meran.
You're most welcome.
Okay, back to the participants. Can you close your PPT, please?
Okay.
Okay, we can see directly. So I back to the participant. Maybe do you have some comment or question to Dr. Meran? Yeah, this is very special for us, right? Okay. Ada pertanyaan Bapak Ibu? Maybe from the Malaysia student, Dr. Peimeng. Have question, Ibu Dr. Peimeng?
May I,
Yes.
may I ask a question?
Yeah, Pak Made.
Thank you.
Yes.
I would like to ask the presenter, Dr. Mehran, did you ever try to measure the amount of hydrogen produced by using your material? I mean, I would like to know the hydrogen production compared to the, for example, the mass of the material you use for some experimentation. Thank you.
Welcome. Actually, already I discussed about the amount of hydrogen production, because the amount of the electrocatalyst that we use is very, very small. For example, just I give you some information. For example, we disperse 1 milligram of electrocatalyst in 1 milliliter. Then we drop 5 microliter of this dispersion on the surface of glassy carbon. 5 microliter of 1 milligram per milliliter. So this is the amount of electrocatalyst. So of course, just we can detect some bubble beside the glassy carbon, beside our electrode. So using this method, I think we cannot, determine the amount of hydrogen production. If you want to determine the amount of hydrogen production, you need the huge cell with huge electrode. So this is the problem. The second thing is that if you want to, determine the amount of hydrogen, you need to attach your cell on HPLC. So you need the extra instrument to measure the amount of hydrogen. So we use on lab scale. Just we try to introduce some electrocatalysts. They have potential for HER. This is our objective. Based on their electrocatalytic activity, based on Toffel law, based on LSV, based on stability, based on durability. Okay, so of course the research in this area is very wide. For example, you can move to photocatalysts. For example, you use the renewable energy or light instead of, for example, electricity and produce hydrogen and test. Or you can use the seawater inside of your electrolyte. So the research in this area is very wide. But my research group only work on the electrocatalytic activity of this material.
Okay. Thank you. May I continue my question?
Yeah, of course, Pak Made. Dr. Meran, can you open your video, please?
Okay.
Yeah, so participant can see you directly. Yeah, the handsome presenter.
Thank you.
Okay.
Go ahead, Pak Made.
Maybe you have one slide for us to show in which part hydrogen will be attached in your material, because you mentioned some 3 or 4 material in your SEM graph. In this process, I'm sorry, I'm new in this topics in this field, so can you show me like where's the place hydrogen will attach in your material?
Okay, so let me share my slide, okay?
Thank you.
Welcome.
Yeah.
Okay.
Yeah.
Okay,
Recording in progress.
you see the graph, Prof? You see the graph?
Yes.
This is the, we call
Yeah.
LSV graph, okay? We scan
Yeah.
from positive voltage to negative. For example, here from 0.1 to negative 0.6. So the voltage increasing, and according to voltage, current also increasing, right? So this current comes from the hydrogen production. When hydrogen produce, the current increase. So when current reach to negative 1 milliampere, means we call onset potential, means in this voltage, okay, hydrogen started to producing. And after that, when the current reached to negative 10 milliampere, so it means that hydrogen production is completed. Hydrogen no produce. This two voltage is very important. Understood? So the voltage related to negative 1 milliampere and voltage related to negative 10 milliampere. These two voltage is very important in the LSV graph. So if this voltage shift to lower voltage, so it means that the hydrogen is produced in lower voltage, right? So it means that the consumption of electricity decrease, right? So based on this voltage, we will evaluate our composite.
Okay.
The composite has ability for hydrogen production. For example, right, and then we will compare with platinum, commercial platinum. Commercial platinum shows the best. For example, for commercial platinum, onset potential is around positive 40 millivolt. So it means that in positive 40 millivolt, the current reached to negative 1 milliampere. And the over potential is around negative 40 millivolt, negative 40 or negative 50 millivolt, not volt, millivolt. You know, so it means that around negative 50 millivolt, the current reached to negative 10 milliampere. So it means that the hydrogen production is completed. You produce the, the higher amount of hydrogen. Based on these two voltage, we will decide this composite has potential for hydrogen production or not. Hopefully you got your answer. And the TOEFL plot shows the kinetic of chemical reaction. This chemical reaction take place with which, rate. The rate is important. The rate of dropping from negative 1 to negative 10 milliampere.
May I ask a question again?
Okay.
Is in this process, do you think this will be absorption or adsorption? It will be adsorption. I would
Adsorption.
So it will attach, right?
Yes.
So in which area, on which part of the, in which side, maybe side, we call side, in which side the hydrogen will be attached in this production? In the MOS2 or the PT or maybe in the supported material?
No. The water adsorb on the surface of electrocatalyst. Hydrogen dissolve.
Yeah.
You know?
Yeah.
So the process of adsorption of hydrogen is called Volmer mechanism, you know? So depends on the composite. Sometimes you have different type of active site. You know, sometimes, for example, some component facilitate the desorption of hydrogen. Sometimes some component facilitate the adsorption of water. So both of them should be take place, in the best way. You know, if, for example, adsorption of hydrogen is facilitated, but desorption is not take place, so the reaction is not completed. So we can see all of this one in LSV graph. So when LSV shows the good voltage at higher temperature, higher the current. So it means that this adsorption and desorption take place and hydrogen is produced. If hydrogen is not produced, you cannot see the effect in on LSV curve.
Yeah.
Understood?
Okay, because I work on hydrogen fuel cell, just like PMFC. In PMFC, the catalyst, the proton will be react with the oxygen in the site where the platinum, what's the name, attached in the carbon, because we use PTC, you know, that we call that's the site where the hydrogen will react with the oxygen. I imagine them something like that, so that's why I ask you why how to produce the hydrogen from the VT or MOS2. Thank you very much.
Welcome, most welcome.
Terima kasih, Pak.
Thank Pak Made. Yeah, I think we have a similar riset, Pak Made. Yeah, hydrogen fuel cell limit.
Oh, bagus lah, Pak.
We can discuss later.
Yeah.
Okay, well, is there any question from participants? So, Dr. Meran, some common people say, in our laboratory, of course, right, we have experience. Oxygen, people not so afraid, not so scared, about the oxygen, gas. But hydrogen, many people very scary, What do you think? Yeah, because this is we need a special storage for hydrogen. Yeah, do you think this is very safety for future if we succeed to make a hydrogen production based on your way, right? So, do you think the storage?
Already I mentioned that we don't have any chance. You know, in future, if we want to move from the fossil fuel to green fuel, so right now the hydrogen is the best. I don't know, maybe in future we found another green fuel. But right now, of course, the hydrogen has disadvantages. Already I mentioned that the price, I think, is not challenged because the price is controlled by others. In future, of course, definitely the price of fuel increase, you know. So about the safety, we have to change the attitude of people. Then we have to tackle this issue, you know. But right now, based on, the research, the hydrogen has potential for commercialization. So of course, still research on finding that, novel and cheap electrocatalysis is going on, you know. But hopefully we find in future good electrocatalysts that replace with platinum. But we don't have any chance, choice. We have to tackle this issue in future. I'm talking about future. For example, in 5th of October this year, the Prime Minister of Malaysia, issued some letter about the importance of hydrogen. And now they start making some company. Because I want to apply for some grant, they asked me for company, and I searched too many company in Malaysia. Still, we don't have some company. They start the production of industrial hydrogen. But no, they understood they have to start. Because Middle East country, of course, they have fuel, but they start the production of hydrogen. For example, Saudi Arabia started already the production of hydrogen. So we have to start. We have to make some company, like, for example, solar cell company. There is some solar cell company, but still in Malaysia, we don't have any, company related to hydrogen production. But this October, the Prime Minister issues the letter, and in Sarawak, they want to open the company for production of hydrogen till 2027. Hopefully, the company industry actually impress for production of hydrogen.
Yes, I agree about that. Because since 2013, already many Japanese company, Japan company, to produce hydrogen, right, by using the steam methane reforming, And a very hot issue in 2013, how about the sodium borohydride? Yeah, convert to be hydrogen, yeah, chemical approaching. So this is very special for me, yeah. Anyway, based on your slide in here, interesting, your catalyst, electrode catalyst, platina PT mixed with molybdenum, right?
Molybdenum disulfide, MOS2.
Yeah, molybdenum disulfide, right? Already close to the red side, red part, yeah.
Yeah.
Already close to commercial, yeah. I think
Yeah.
this is very interesting data, yeah. But this is maybe a commercial using Matthew company. Usually they use carbon black, right?
Yes.
Yeah.
20% platinum and carbon black.
Have you calculated comparing your electrode catalyst? This is cheaper or?
Yes, definitely, definitely. First of all, regarding the amount of platinum they use in molybdenum disulfide is 10 times lower than commercial PT they use.
10 times.
10 times, yes, the commercial PT. About the content of platinum on the composite compared to commercial carbon.
Yeah, interesting.
Yes,
yeah. Okay, participant, yeah. Do you have a question to Pak Meran? No question? Yes.
Can I ask some questions?
Yeah, Pak Ron. Time is yours, Pak.
Dr. Meran.
Yes.
How are you?
Hello, thank you so much.
Okay. Just some notes probably. My group before we work on very thin surface of platinum, for example. So we use techniques called atomic layer deposition. Then that will produce atomic thin layers catalyst on the surface of the whatever substrate we want to use. And I trust that will be the one of the method that we can reduce the cost, because we only use a very thin layers. But I got two questions for you from the presentation. Number one, regarding the stability of the catalyst, because a lot of time there will be some catalyst poisoning. So do you observe this in the catalyst? That's the first question. Second question is that related to HCR, at the anode we have OER, right? And I think the issue now mainly is in the OER side, not on the HCR in terms of kinetics, right? So OER sometimes become the limiting reaction. So there's a lot of works on the bifunctional catalyst. So it's the same catalyst you can use both from HCR and OER. So maybe you have any comments on that? How are we going to design the catalyst based on some fancy materials, or like what you say, beyond graphene for this purpose? Thank you, Dr. Meran.
You're welcome. Actually, yes. Actually, OER also play an important role in this reaction, because if OER doesn't take place, the whole reaction is not completed. But already because I'm not expert in OER, but already I have some study about the OER. They claim that in alkaline media, they found the cheaper material for OER. Still in alkaline media that have potential for commercialization. No, most of industrial large-scale hydrogen is produced in alkaline media. So for alkaline media, no, they don't have problem with OER material. So they found the cheap material for OER. They have potential for OER with high electrocatalytic activity. But still in alkaline media, they couldn't succeed to find the good material for HER. Still the challenge for HER. I don't know, because I don't have any experience with OER. I'm working on HER. But I read in some article, they claim that in alkaline media, especially in alkaline media, OER is not challenged, because no, they found something for OER. Still for HER is challenging.
That is the issue, because HCR we
Yeah.
normally do in the acidic conditions, and OER actually good in the alkaline conditions.
Yeah.
But I think we should soon move to the OER. Like it or don't like it, I mean, there is the direction to go, because HCR, I think many catalysts has, I think, is able to very close to the perfect catalyst in PT, right? Yeah. So yeah, I thought that maybe there's some ideas, how we can brainstorm to achieve maybe a good OER catalyst, or better still, we have better good bifunctional catalyst. Right. That would be fantastic. Thank you, Dr. Meron, for your
Most welcome.
presentation.
Most welcome.
Thank you.
Thank you. That's good.
Thank you, Baron.
Welcome.
Any question, participants? Okay. So, meanwhile, to wait the participant, Pak Meran, Dr. Meran, can you share also your presentation to the chat, please?
Stop sharing.
Stop sharing and
Okay.
please share your PPT to the chat. Okay. So, any question? Ibu Hermania from ITV, do you have a question, Ibu? So Dr. Meran is very expert, I think, in electrochemistry. Yeah. He is very well to present the result, I think. And this is a very special, I think, for your master student. Yeah. Recently you provide catalyst by using CVD, right?
Yes. Right now they are working on CVD. Two of my students and Dr. Gola.
Yeah. Of course, in CVD you have to use the gas, right?
Yeah. But
And
unfortunately,
also,
already mentioned that in CVD the control of, purity is so difficult.
yeah. And
So
I think this will increase the cost, of course, right? Compared to we use the very simple preparation of catalyst by using the styrer, and room temperature, And what do you think? This is a best, maybe different the case, right? In our case, if we use the catalyst like Pak Made case, in a fuel cell catalyst, platina, right? This is we have to think deeply many conditions, because platina sometimes direct suddenly be agglomerate like that if a high temperature, and also some of carbon black will be aggregation, right? If 600 degrees C. That's why previously we don't favor to use the high temperature for preparation of catalyst. We use chemical like ethanol, and all done in room temperature. So this is very interesting for me. Your data is very nice based on the TM. Even you use a CPD, right?
Yeah.
So
yes.
my question: do you control some treatment in CPD to make
Actually, to tell the truth, we need the perfect CVD machine. We are looking for, I don't know, we have to buy or we have to improve it, because you know that when you want to, for example, synthesis the molybdenum disulfide, you need the 3-position temperature zone. The sulfur melting temperature is completely different than molybdenum oxide melting temperature. And the formation temperature of molybdenum disulfide is again another challenge. So I think it's better you design the CVD with 3 different zones. zoom temperature, because you leave the molybdenum oxide one side, you leave the sulfur another side, and you leave the substrate between these two components or top of some of them. Then the sulfur evaporate, the molybdenum disulfide evaporate, and the molybdenum sulfide form on the surface of substrate. So the temperature of formation of molybdenum disulfide is different than melting temperature of sulfur, different than melting temperature of molybdenum oxide. So briefly, you need 3 different zoom temperature. So our CVD machine can control only 2 zoom temperature, you know. So I think the ideal CVD machine for production of TMDS should be at least controlled on 3 different zoom temperature. So if you control the temperature in 3 different zoom, 3 different temperature in 3 different zoom, then I think the quality of sample definitely will increase. So right now, unfortunately, our CVD machine just controlled by 2 temperature, but still the result for monolayer is nice. But in Raman spectra and XRD, we have purity of molybdenum oxide, especially in Raman spectra, of course in XRD, yes. But in Raman, still we have some impurity in system, and we try to produce the monolayer of molybdenum disulfide with high impurity, with high purity. This is the challenge in CVD, in our CVD. I don't know, because already around 4 years ago, I had visiting in NTU, National Taiwan University, under the collaboration with Prof. Chen. He is very expert in CVD, the grow of different material using the CVD. Their CVD work with 3 different zoom temperature, and they produce very high quality and high pure different type of 2D material, like tin sulfide or like. Okay. This is the challenge. This is the challenge in our research right now.
And Dr. Meran, you use the precursor platina, right? So yes. You use a powder precursor of platina, right?
Actually, we use chloroplatinic acid solution, H2PtCl6.
Okay. So this is a powder or liquid?
No, this is like a liquid. This is the solution, chloroplatinic acid solution. Then they disperse, for example, 10 microliter of this one inside of, they mix with molybdenum disulfide. They synthesize molybdenum disulfide using hydrothermal. And after that, in temperature around 70 degree or 80 degree, they use the chloroplatinic acid solution with some reducing agent, like a hydrazine. Then just 24-hour mix this platinum precursor in the presence of reducing agent for 24 hours mixing, just simple mixing.
Okay, I see.
And,
So the question is how to make sure you already have a platina zero valent.
Because we use the actually reducing agent, and then XRD graph shows because in this slide I didn't add some XRD because in their paper everything is completed. So you can see the XRD, the Raman, the XPS, many characterization. But XRD shows the existence of PT, platinum peak in composite. And also the XPS also shows that there is the platinum in composite, exists platinum. And the size also very, very small. You can see using the TM, the size of platinum was around 2 nanometer.
2 nanometer.
2 nanometer, yes. Yes, and the agglomeration also is not very high. But when Mina increased the concentration of the platinum precursor, she observed this agglomeration. Again, in her paper, you can see other TM image. She saw some agglomeration in molybdenum disulfide surface during the formation of platinum.
Okay.
May I continue?
Yeah, Pak Made. Okay, okay.
Dr. Meran,
Yes.
do you have any idea do you mean small amount of platinum? May I know weight by weight for the platinum loading in the your material?
Already I discussed with Prof. Rickson. You know, we use the simple method. We use the chloroplatinic acid solution, H2PtCl6.
Yeah, I understand that. I mean, you said more platinum will be increased possibility to agglomeration.
Yes.
Yeah.
Yes.
In which amount for the weight base maybe basis?
My student start from 5 microliter till maximum 100 microliter H2PtCl6.
To 100 microliter.
Yes, he synthesis maybe around, for example, 20 different composite. 20 different composite. Start from 5, 10, 20, 30, 40, like this. And then she tested for electrode, for HER. And she observed till 60 until 90, the result is very nice. But after 90, the result become constant or drop. And she continued till 120 microliter. Start from. So she optimized 60, 90, 120. She observed that after 90, the agglomeration increased and agglomeration started because she didn't see any improvement in LSV or decrease in LSV.
Okay, thank you.
You're welcome.
Okay. Pak Made, we can collaborate with Pak Dr. Meran.
Thank you.
I will highly appreciate if you give me a chance to collaborate with you.
This is honor. This is my pleasure. This is my pleasure.
We open our hand to collaborate with you, with Pak Made. Yeah.
This is my pleasure.
Okay.
Yes, saya dari Udayana, Pak. Prof.
Ya. Oke, nanti saya minta dari Ibu Ibu Puji ya nomornya ya.
Iya, saya dapat dari Ibu Puji.
So Bapak Ibu silakan isi ininya ya, absennya. We provide for you the certificate as well as our appreciation for your precious time to join with us in this webinar.
Thank you so much.
Okay, we still have a time, yeah. Is there any question from the participants? Yeah. Ibu Irwana, do you have question, Ibu Dokter?
So far, it was so clear. So thank you.
So clear. Okay. Student also some PhD student from the chemistry join with us in here. Do you have a question to Pak Meran, to Dr. Meran? Okay, Ibu Lisnawati, Dr. Lisnawati, do you have question, Ibu? So, Dr. Meran, you also use the silica, right?
Yes, manganese silicide.
Okay, so Dr. Lisnawati, her PhD, producing the silica from the fire mountain. Yeah. Any question, participants? We have 6 minutes, 6 minutes else. If you have a question. Yosia, do you have question to Dr. Meran? Yosia?
Yes, Prof. I think for now it's not the. Thank you.
No question, yeah. So the last question from me, Dr. Meran, yeah. So of course the graphene, yeah, problem in band gap, right? You know well about that. Yeah, valence band and conduction band. There's no gap, yeah, between in graphene case, right? However, many people try to open the gap by using the nitrogen or boron or sulfide, right? So do you think graphene is still a prospect for future to decrease the platina loading, for example, or the other application? What do you think?
Actually, Prof, the graphene lonely didn't show the good electrocatalytic activity. They
Yes.
use as a supporting material, improving the electrocatalytic activity of other material, you know. Maybe it doesn't have potential for producing the active site. So of course, graphene is very nice, but I think we have to always focus on the potential of material. We improve that potential. For example, if some material doesn't show the potential for HER, we have to leave it.
Okay.
We have many choices. We have to find some material that has potential for this one. For example, molybdenum disulfide has potential. We have to focus on molybdenum disulfide and improve molybdenum disulfide efficiency, right? So right now, graphene didn't show the, for example, good electrocatalytic activity. Of course, in composite shows the good electrocatalytic activity, improve the electrocatalytic activity of material, but lonely didn't show good electrocatalytic activity. Yeah, but graphene has other potential. For example, in optoelectronic device, in solar cell, we can use it. And for example, convert the non-conductivity of substrate to conductive substrate. For example, right now in solar cell, we use ITO, right? ITO is glass that coated with indium tin oxide. So maybe in future, with very thin layer of graphene, we can substitute graphene with ITO, you know, because graphene is transparent and also conductive and very light and very strong and very cheap. So we can substitute with ITO. So I believe that we have to, consider the material based on their potential for application. Sometimes this is just discussion. Sometimes we bring everything in any application. For example, in HER, you see many, for example, research about different type of material. But most of them doesn't have potential. Just they want to introduce some application for their material. But I believe that we have to focus on application. Focus on application and try, based on application, find the material that have potential for this application. Not we focus on material and then find application that suit for this one, you know? For example, I'm working on HER, right? So I have to try to find good material for HER. Not, for example, I synthesize something and then say, okay, this one also has potential for HER. Of course, show some efficiency, but they are not perfect. You know, this is the challenge. We have to solve this challenge. We have to find some material that suit for this application. Yes, if we want to use, for example, graphene, we can use as a composite, as a supporting material, beside other material. For example, one of my research group on working on cobalt selenide. So yes, or for example, cerium oxide. So they are trying to synthesize this novel material, you know, cobalt selenide or cerium oxide. The research shows that they have potential for electrocatalysis, but we can improve this material using graphene as a supporting. But graphene only doesn't show good electrocatalytic activity for HER.
1 minute, Prof. Iksan.
Yeah, Pak Made.
1 minute. Dr. Mehran.
Yes.
Right now, I work on to produce MEA in PMFC, membrane electrode assembly. Maybe similar to the problem of the PT. So I would like to reduce the loading of VT on the membrane, on the catalyst. I have an idea to reduce the PT by using lightweight metal. Do you have any suggestion, or maybe your knowledge, maybe no, or maybe I would like to reduce the PT by using titanium, something like that. Do you have any
as a supporting?
No, not supporting. We would like to the supporting is carbon or maybe graphene,
Okay.
reduce graphene, RGO. So PTTE, platinum titanium supported by reduced graphene. So that's why I would like to reduce the loading VT by using by substituting some of the VT with the PT with the titanium. Do you have an idea for the lightweight metal that we can use to reduce the PT?
So, Prof, recently I read a very nice paper in Nature. They reported the growth of single crystal platinum on the surface of fullerene. Yes, fullerene is look like CNT, like the family of graphene or carbon.
Carbon nanotube.
So yes, they report very nice efficiency for HER, especially in alkaline media. And they claim that the single crystal of the platinum compared to, for example, some other type of morphology or like that, the efficiency improved. And I can send you this paper. I think this is very nice for production of the platinum, single crystal platinum. They for example, compared to cluster or like that, they claim that. But I think the synthesis method of platinum also play an important role.
I see.
You know,
yeah.
I think, but yes, but I don't know. We have to test it. This method is nice or not. Because control of crystallinity of platinum also is important factor. They report like that. Recently, this paper published in 2023, single crystal of platinum on the surface of fullerene.
Okay. Dr. Meran, I give you 1 minute to share your PPT to the chat. Yeah. So could you do it? Yeah.
You need to share the PPT?
To the chat, because to Zoom chat, because many participants request it.
Okay.
Still a question from the participants?
There is not any. I cannot see any question, Prof.
No question.
Or maybe,
maybe. Please share your PPT this morning. Yeah. To the chat. Yeah.
Share this PPT.
Yes.
Maybe I
your
can.
PPT file. Yeah. Your PPT file, please.
Okay. Share here. Okay. Wait. Okay.
So participant can download by themselves, right?
Okay.
Okay. Is there any question, participants?
So, Prof, how can
you choose the chat?
Yes,
and then
I use the chat, but I cannot find the upload file upload.
File, please choose file, and then
cannot see the file here.
The bottom icon.
The bottom
in
the bottom icon.
Bottom icon or in bottom. Bottom.
Yeah.
No. The bottom.
Close to the motion. Otherwise, you can send to my
WhatsApp. I can send to your WhatsApp, you please, if possible. Okay, wait. I send to your
and then
WhatsApp.
I send to the.
Yes, you can send in group.
Please do it before we close. Yeah. So participants can receive your PPT, Dr. Meran. Okay. Meanwhile, we wait. Dr. Meran send his PPT to me, right? Okay. Yeah, not yet.
Prof, done.
Already?
Already done.
My up?
Yes, need a time to upload. Okay, I think done.
Okay.
You see?
Yes.
Okay.
Yeah. Okay. Okay, just a minute. Yeah, I will share to. Okay. Okay, already. All the participants can download directly from the chat. In our chat Zoom, I already share Dr. Meran's PPT. And also please fill in the presentation absentee link. Yeah, based on that, we provide a certificate and directly send to your email. Really sorry if you didn't fill in the link absentee, we cannot provide a certificate for you. Yeah. So once again, I remind you, please fill in the link presentation, link abstention, sorry. And then in this week, you will receive your certificate. Okay. Finally, due to the limitation time, yeah, we appreciate high appreciation to Dr. Meran, yeah,
Thank
who would like to share his knowledge and his experience, yeah, especially for hydrogen production to all of us, yeah. So I believe we can catch the many things, yeah, as well as our spirit again to do the research and to take some important information from Dr. Meran, how to prepare the catalyst and how to analyze the catalyst based on electrochemistry. Of course, this is not the last for us. Yeah, we can communicate many times also with Dr. Meran. I think he is very happy to discuss later about our topic this morning. So all participants, I would like to introduce, this is the equity program launched by our LPDP minister, yeah, Menteri Keuangan, LPDP, Finance Minister, yeah, supported by them. That is called the program Equity. So in this equity funded by Finance Ministry, our goal, our Universitas Sumatera Utara may be improve their rank in World University rank. That's why we will provide many webinar, guest lecture, yeah, and invite the top scientists from the world around the world. Yeah, one of them is Dr. Meran. So hopefully we keep contact Dr. Meran, and please we will choose you as well as one of surveyor, yeah, to submit to KSWUR rank. Yeah, hopefully you will receive the email from KS, and please say our university is the best university in the world. Yeah. Don't forget to respond the KS email. Yeah.
Okay.
We will request to them, and one of the surveyor, we request your name. We will submit to them. Yeah. Again, thank you so much, Dr. Meran. Yeah.
Thank you, Prof.
Yeah.
Thank you for your time.
I am very happy. Yeah, you would like to join with our webinar top scientists this morning, and we will provide many activities. Hopefully you also would like join with us. Yeah, not only for this morning, but for the other day, we can join again and discuss again many things about the research, about the rank, about the publication, and etc.
Sure.
On behalf of our Director of Internationalization and Global Partnership and our Rector of Universitas Sumatera Utara, thank you so much, Dr. Meran, for your nice
Most welcome.
presentation. And all the participants, thank you so much for your precious time and join with us in this morning. Be safety and always the best for all of us in our work in the university and wherever we do, we can produce the fruitful things. Thank you so much. We
Thank
have
you so
to
much.
end this webinar this morning, and before we close, please open your video, please. Then we will take the picture, yeah, as well as our file. For future, we can contact and we can know each other, yeah. Okay, sorry, please open your video, please. We have 2 slides. Okay. Okay, please give the best smile from you. 1, 2, slide 1, 1, 2, 3. Thank you. And second slide. 1, 2, 3. Okay, thank you so much.
Thank you. Thank you.
See you next time. Bye, Dr.
Bye.
Meran.
Thank you. See you. Thank you, Prof. See you. Bye. Thank you. Thank you so
Thank
much. Thank you,
you,
everyone.
Prof.
Thank you.
Rickson. Thank you, Dr. Mehran.
Most welcome. Thank you so much for coming.
Bye-bye.